Okay, now one thing to keep in mind is polynomials are defined for all values of x, but power series are only defined for the values of x that are on that interval of convergence. Okay, so the properties of the polynomials will only carry over to that interval of convergence for power series. Okay, now let's say we have a power series that defines a function f on some interval of convergence I. Okay, so the function f is that power series on that interval. F is continuous on that interval, and the power series can be differentiated or integrated term by term, and you'll get a new power series that's also defined on that interval of convergence. Now, the interval of convergence, you don't necessarily know about endpoints. All you know for sure is that inside of that interval of convergence, that new power series will be defined for. But you can get a new power series by differentiating or integrating a series that you already have. And you just integrate term by term. Okay, so now let's look at our power series that we know, 1 over 1 minus x, and we know that that's 1 plus x squared plus x cubed plus dot, dot, dot. And the interval of convergence is all x between -1 and 1. I want to take the derivative of the power series. And I'm going to take the derivative in each of these forms, just so you can see what it looks like in each form. The derivative of on the left, if I rewrite that as 1 minus x to the -1 power, I can use the power rule, so the derivative would be -1, 1 minus x to the -2 times the derivative of the inside, which is another -1. So that's the derivative on the left. Now the derivative in the summation form will be the sum k times x to the k minus 1. Now, got to be careful here. We started with an index of 0, so the first term was actually this constant term. But now when we don't keep that same counter, because if we put in k equals 0, we'd have a -1 power. And I know that the derivative doesn't have a -1 power. Remember, if you took the derivative of this, it would be 0, then we would have a 1 for the derivative of this. So we need to start with a 1 power on the x, a term that's just the number 1. So I need to change my counter to just 1 here. So when you take the derivative, you're going to need to raise that counter by 1 to make sure that it actually is the correct derivative. So we'll have k times x to the k minus 1, and now the counter's from 1 to infinity. And now doing it term by term, the derivative of 1 is 0, the derivative of this x will be 1, the derivative of x squared will be 2x, then plus 3x squared plus dot, dot, dot. And now the interval convergence, we know, will have at least absolute value of x less than 1. So we have the power series then, 1 over 1 minus x squared, represented by this power series, x to the k times x to the k minus 1, from 1 to infinity, or just represented in expanded form this way. Okay, now let's check the endpoints and see if it actually exists there. If I take this power series representation here and put in x equal to -1, I would have the summation of -1 times, I'm putting it in for the x, not the k. I would have -1 to the k minus 1 times k. If I look at that expanded out, I'm going to have alternating signs. The first one's going to be positive, so I'm going to have 1 minus 2 plus 3 minus 4. Does that converge? No, that doesn't converge. In fact, the nth term doesn't even go to 0. But that does not converge, so this diverges. Now let's let x equal +1. I would have the sum of +1 to the, I'd have 1 to the k minus 1, so that's just going to be a 1. I would just end up with the summation of k, which would just be 1 plus 2 plus 3 plus dot, 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 which we also know diverges. So the interval of convergence here is just the interval from -1 to 1. Okay, so we've got a new power series here. Okay, now let's integrate term by term. So I'm going to take the integral of all three forms here. The integral of 1 over 1 minus x Then I'm going to integrate, so I'm going to look at the summation of the integral of x to the k. And then I'm just going to integrate term by term. Okay, so the left side, well, the integral of this is, I'm going to let u equal to 1 minus x. Notice the du is a negative 1 dx. So when I integrate, I'm going to get a negative natural log of the absolute value of 1 minus x. Don't worry about my plus c's. Equal, integrating term by term, I'm going to have the summation. I might have to adjust my counter here. The summation, the integral of x to the k will be x to the k plus 1 over k plus 1. Okay, now let's see, what should it start with? If I integrate this other form, I'm going to have x plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4. So that one's easy to determine. So now I need this first one to end up in the summation. I need that to end up with having an x to the first power. So the k is going to have to start at 0 here. And so that would be x to the 1 over 1, and okay, and so on. So that would be the form. Notice I just got a power series representation for negative natural log of 1 minus x, which that means I know the natural log of 1 minus x would be the summation of the negatives, x to the k plus 1 over k plus 1, or just negative x minus x squared over 2 minus x to the 3rd over 3. Okay, and my integral convergence here again starts off with the absolute value of x less than 1, same as one as we started with, but let's check the endpoints. If x is equal to negative 1, I'm going to have natural log of 1 minus negative 1, so natural log of 2 equal, and then I'm going to have a summation of, see I'm putting in negative 1, I'd have negative 1 to the k plus 1 over k plus 1, which this is our alternating harmonic series. So this converges. And actually it converges to natural log of 2. So if you took that form on the right and plugged in negative 1, you'll find out what the natural log of 2 is going to be. Now let's look at x equal 1. We're going to have natural log of 0, which doesn't even exist, but let's not worry about that. So I would, since it's going to infinity, I would expect this one not to converge. I will have 1 to the k plus 1 over k plus 1. So this is going to be the summation of 1 over k plus 1, which is just like our harmonic series. So we know that this one diverges. So the convergent interval here will be from negative 1 to 1. So that was our interval convergence. But we've got a new power series now, and this one's going to be very helpful in a little bit. We know the natural log of absolute value of 1 minus x is equal to that infinite series. Okay, and just before, so we don't forget that. See, these were all negative. Okay, be sure we got that exactly right. Minus, yeah. Okay, this first one. If I want to try to get a power series representation for inverse tangent, I've got to figure out how can I get that from some of the things I've already looked at. So can I, we've tried integrating, differentiating 1 over 1 minus x. It didn't get inverse tangent. But we did have one that was a 1 over 1 plus x squared. Let's see, inverse tangent, I know what its derivative is. I know that the derivative of inverse tangent is 1 over 1 plus x squared. If I integrate 1 over 1 plus x squared, I get inverse tangent. So let me start with that fact. Think of what you might know about inverse tangent and write it down. Now, the integral of 1 over 1 plus x squared, we can come up with the power series representation for this function just using our 1 over 1 minus x. And we came up with that one earlier. Okay, so now if I put in the minus x squared in place of the x, I've got 1 over 1 minus x, or 1 plus x squared will be 1 minus x squared plus x to the 4th minus x to the 6th. I'm putting in the minus x squared, so it should be an alternating sign, and each time the powers are even. Okay, so I'm going to use that and substitute it in on the left side. So I've got the integral of 1 over 1 plus x squared equal the integral of 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th, and so on. And this is going to give me a power series representation for inverse tangent, because I know the integral of this function is inverse tangent. So integrating term by term, I get x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9th over 9. Okay? So that would be an infinite series representation, a power series representation for inverse tangent. Now, we integrated here, so we do have a plus c involved here. Let's see if we can find out what that plus c is. I know if I put in x equal to 0, I have inverse tangent of 0 equal, now all these terms are going to be 0, and so we should have that equal to c. Inverse tangent of 0 is equal to 0. So this should just be 0 here, so we don't have to worry about that plus c. So we've got inverse tangent of x minus x cubed over 3 plus x to the 5th over 5. And there's our power series representation. Okay, now this one, I'm going to use the fact that natural log of 1 minus x is equal to that. Okay, now I didn't check my interval convergence on the last one. Let's go ahead and do that. Okay, now this was actually the integral of the summation of the x sub 2k's, starting at k equals 0 to infinity. So if you took the integral of that side, you also got the other form, the summation of x to the 2k plus 1 over 2k plus 1. And you can also just read that off of this. And then I have my alternating sign in there, minus 1 to the k plus 1 to the kth power. Okay, so this is the other way you could write that, using the summation notation. So now if I want to check the interval of convergence, I know it converges on the interval from minus 1 to 1 because the original one up here did. So now checking the endpoints, I would plug in the 1 and negative 1 into this expression over here. Let me get rid of this. We'll come back to this in just a minute. Okay, I'm going to have the summation of negative 1 to the 2k plus 1, negative 1 to the kth over 2k plus 1. I'm just trying to see if this converges. The negative 1s, I can add the exponents, and so I get a negative 1 to the 2k, 3k plus 1. So it's still going to be an even or odd number. Now this negative 1 to the k, it's easier probably if we think of this way. Think of this as our alternating sign, and this is the value of x. We're going to have that alternating series here. That if we use the alternating series test, that tells us that as long as that kth term is going to 0, that it's going to be convergent. As the kth term, which is the rest of this stuff, goes to 0, and it will as k gets larger and larger, then we know it's going to converge. So as long as we keep this alternating sign there, we will have that this thing converges, and it will converge then if the x is 1 or negative 1, because this is our x to the k, 2k plus 1. So as long as this term, keep this alternating series, and as long as the rest of this thing goes to 0, we do have the limit of that a sub k term going to 0. So that means it converges at x equal -1 and at x equal 1. So it will be convergent. The interval of convergence will be -1 to 1. Okay, so now let's get to that last one again. We saw that the natural log of absolute value of 1 minus x was equal to negative x minus x squared over 2 minus x cubed over 3 minus, and so on. So I'm going to form this new one by looking at the log and separating this off into two expressions. This is log of 1 plus x minus log of 1 minus x. Just using a property of logs. From the fact that log of 1 minus x is this one, I can put in a negative, use a negative x for the x, and I have that natural log of 1 plus x will be, I'm putting in negative x everywhere the x's appear. Okay, which gives me a positive x. I'll have negative x squared, so it's going to still be negative x squared over 2. And then I have negative x cubed. We'll have a negative there and another negative, so it'll be a plus x to the third over 3. So let's see, does that make it, I'm still going to end up with that alternating sign each time. So then it's going to be a minus x to the fourth over 4, and so on. Okay, so taking this difference then, I'm going to have x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4, and then subtract off this one, which is the original one, negative x minus x squared over 2 minus x cubed over 3 minus x to the fourth over 4. And then notice that some of the terms are going to cancel. I have a minus x squared over 2 here, and this one's going to actually be a plus x squared over 2 when I distribute my minus sign through. So I'm going to end up with 2 times the x. This one will be duplicated here and here. And we'll have an x cubed over 3 here, and this will be a plus x cubed over 3. So x cubed over 3. The x to the fourth will cancel. There's that negative one. That one's going to be plus when I distribute the minus 1. And then I'm going to have plus an x to the fifth over 5. Okay, and that would be the representation then for natural log of 1 plus x over minus natural log of 1 minus x, which is natural log of 1 plus x over 1 minus x. Now we formed this power series from summing or taking the difference of two power series that we already knew. So when you do it by summing or differencing two power series you know, it will have the same interval of convergence. So our interval of convergence will be the same as we had for the natural log of 1 minus x, which was the interval from -1 to 1. So we don't have to worry about checking endpoints unless we're differentiating or taking the integral. If you want to write the summation notation for this one, this summation notation, this is 2 times the summation. X to the 2k plus 1, you can always represent an odd number. Notice the exponents are odd. 2k plus 1, and the number on the bottom is matching that exponent, and that's from k equals 0 to infinity. And I think that's it. So these are all the same, just in different forms. And so you can get new power series by differentiating, integrating, taking sums, taking differences, and you just have to be creative how you what you use, because all these started with that one power series from that geometric series. The 1 over 1 minus x is 1 plus x squared. That's our initial power series that all these others are built on.